All right, so let's begin. We're going to continue our discussion on convolutional neural networks. Here's where we're going to do. We're going to look at back propagation through convolutional neural networks to learn about how we can train all the components of a CNN. In the next class, we look at the other topics that we have on my list. So here's the story we have so far. We've seen that pattern classification tasks like does this recording include the word hello are best performed by scanning for the target pattern. Scanning with the input with a network and combining the outcomes is equivalent to scanning with individual neurons hierarchically. First level neurons scan the input, the next level neurons scan the outputs of the first level neurons, and so on. And a final decision unit or layer can make the final decision. Deformations in the input can be handled by pooling. For two-dimensional or higher dimensional scans, the structure is called a convolutional neural network, or ConvNet to be short. Do you mind shutting your laptop? Yeah, thank you. Right. And for 1D scan a long time, we called it a time delay neural network. So here was the general architecture of this ConvNet. We had convolutional layers comprising of neurons which scanned the union of all of the maps in the previous layer, and pooling layers which comprising of units which sort of only locally scanned one map and try to introduce some jitter invariance. In a convolution layer, each output map, a convolution layer had comprised of a collection of output maps or channels. We also call them channels. And each output map the computation of each output map had two stages. And the first stage, we computed an affine map by convolving a filter over all of the maps in the previous layer jointly, and following which we applied an activation pointwise to every element in the affine map. Nihar, do you mind coming up front? Okay. So, and here's how we actually perform the computation, just for a quick recap. Again, we're going to need all of this. So we'll do this now. We'll go over this. For each output affine map, we had one filter, and the filter itself had as many planes or channels as the number of input channels, or the number of input maps. And so here, for instance, the first map here might be composed of the first filter, the second from the second filter, and so on. And so if you just looked at the overall computation, here's what it looked like. In order to compute, say, this first map, you would place this first filter on the input maps. Guys at the back, can you come up front, please? So, and scan the input. And at each point, we basically computed an inner product, which is a pointwise product of the filter value and the value of the map underneath, and then we summed over the entire lot. The summation, of course, went over all of the maps. Within each map, you went over the area of the filter, and at each position, you multiplied the filter value, which is shown by W over here. This notation, please note it. W, L, M, N, I, J. It has many indices. The L represents the layer for which you're computing you have the filter. The M is the index of the input map or the input channel. The N is the index of the output map or the output channel. And this I and J are positions within the filter itself. So we would place this filter at some location. And then, so if you place the filter at XY, location XY on the input map, then each filter index is going to be added to the index of the Y map itself to find the location at which the filter value applies, right? And so this one here, it looks complex, is basically a pointwise product of the filter value at each position and the map value underneath. You'd sum this over the face, and then which is this inner product, inner summation, and then you'd sum it across all of the maps, which is the outer summation. There could be an additional bias, and this is going to compute the affine value. You do this at every position, scanning the input in order to compute the output. And once you computed this affine map for any filter, you would apply this pointwise activation to compute the final activation map for that channel. And so, more explicitly, if you had a whole collection of filters, every one of these input channels or the input maps is going to be used in the computation of every one of these output maps or output channels, affine maps. And there, each map again is obtained through the application of the corresponding filter. Can you come up front? So, and once we compute these activation maps, these affine maps, we apply the activation pointwise to compute the final output activation map. So this was the computation. Here's your first problem. Ten seconds, guys. Okay, does anyone on Zoom want to answer this question? Is anybody on Zoom?
Yeah, they have answered 1, 4.
1 and 4. What about you guys? Which do you think are the answers? 1 and 4, okay, right. The number of channels equals the number of input maps, right? The number of channels in any filter. And the number of filters equals the number of output maps or output channels, right? So we also had this additional pooling layer, which could intermittently follow the actual convolution layers. And those pooling layers basically looked at aggregated values in a small window. So if you were performing max pooling, the max pooling window, max pooling filter would look at a small square region of the input and pick the largest value and scan the input with this max operation. So if I were to write the pseudocode for it, again, the pseudocode is kind of important for this, for the filtering, for the pooling operations, because we'll use it later. This is a one-to-one computation corresponding to each input map would be a max pooling filter, which is going to scan the input left to right, top to bottom. At each position, it finds the index of the location within the window, which has the largest value, and then it's going to just read the value at this location off for the output. We also had the mean pooling, which was basically the same operation, except instead of picking the maximum value, you were actually computing the mean. Do you mind shutting the laptop, please? Okay, so, and here the code is basically the same, except that instead of, it's an even simpler piece of code. Instead of finding the index of the maximum location and then copying the value over, you just sort of computed the mean of the values in the window. Now, we also had resampling layers, which could proportionately increase or decrease the size of the maps. And so downsampling, if you downsample by a factor of S, it would mean that the output is going to be a factor of S smaller than the input on each dimension, which means that after each column, you just drop the next S minus 1 columns. After each row, you just drop the next S minus 1 rows. Similarly, upsampling by a factor of S means that the output is going to be larger by a factor of S approximately along each dimension. I'm saying approximately because of edge effects, which can add a little jitter. But basically, when you upsampled by S, it meant that after each row, you added S minus 1 rows of zeros. After each column, you added S minus 1 columns of zeros. So this was what downsampling would do. If you were downsampling by a factor of 2, this is the equivalent of saying, I'm just going to replace all of these blacked out values, every second row and every second column, by zeros. Basically, there's an operation in between here and here, which just says all of these values are zeros. And then the next step is I'm going to throw them all away, right? And so upsampling, it's the exact reverse. You're going to go from here to here, right? So you would just be introducing zeros between rows and columns. Now, typically, when you perform downsampling either follows a convolution layer or downsampling follows a pooling layer. And in this case, instead of having two distinct steps of convolution followed by downsampling or pooling followed by downsampling, you can achieve the same effect by performing the convolution or pooling operation with a stride greater than 1. And upsampling, again, after upsampling, you would not be followed by a pooling layer because pooling over a bunch of zeros is kind of a meaningless operation, right? So, and you could lose information in the process. So typically upsampling is only followed by convolutional layers. And once again, you can think of this combination of upsampling followed by convolution as convolution with a stride, if you are with a fractional stride. If you are upsampling by S, then the stride is going to be 1 over S. And so this is also often called transpose convolutions for reasons we won't get into over here. It's just convenient to think of it as introducing a bunch of zeros and then performing convolutions. So just to summarize, when you're performing operations with resampling, the resampling is generally merged with either the preceding or the subsequent layer. If you're downsampling, you're merging it with the preceding operation, where the preceding operation is done with a stride greater than 1. If you're upsampling, it's merged with the subsequent operation, or thought of, can be viewed as being merged with the subsequent operation, where you're performing that operation with a stride less than 1. So finally, to recap, when we put all of these together in a CNN, for say a typical image classification task, we'd start off with a bunch of RGB images which you could stack, and then you'd have a sequence of convolution and pooling layers. The convolution layers would have their filters. The pooling layers basically, of course, they're performing fixed operations. They're like was it the S or the C planes in Fukushima's model? C cells, right? They don't have learnable parameters. And so these are just fixed operations. Then at the final output, you would have a collection of maps, but then you could unravel each of these maps and flatten the entire set of numbers into one large vector, over which you could have compute an MLP. So when you're speaking of learning the network, you're speaking of learning all of these filters and the parameters of this MLP. Now, training is, as in the case of a regular MLP, the only difference is in the structure of the network. The training examples are provided where each training instance is going to be a data instance and the class. So if you were performing, say, face detection of faces, or recognizing faces or recognizing objects, you would have a collection of images of the objects and the class ID. Now, if you were performing object recognition, is it now necessary for the object to be centered in your picture? Why not? We have position invariance. That's the whole point of the model, right? So the way we would do it is we define a loss, define a divergence between the desired output and the true output of the network. This aggregates the divergences over the training, and then the loss aggregates the divergences over all the instances in the training set. And the network parameters are trained to minimize this loss through gradient descent, where gradients are computed using back propagation. So first step, you define a loss. For each training instance, you pass this through the network, and then you have the desired output of the network for that input, so you can compute a loss for that instance, right? And again, training, you're given a collection of input-output pairs. You can compute this divergence for each training instance. The loss is simply going to be the average of these divergences over the entire training set from which you're learning the network parameters. So here is the loss again. It's the average of the divergences over the training set. The derivatives are of the loss with respect to any parameter is the average of the derivatives of the divergences for the individual training instances with respect to that parameter. And this is what we must compute using backprop. And we know how to do this for a multi-layer perceptron, right? Easy enough. So you can compute those derivatives all the way back to this first flattened layer. But then the thing to remember over here is that the flattened layer itself, that flattened vector was simply composed by, say if I had something of this kind, A, B, C, D, E, F, G, H, I, and then the next map would have J, K, L, and so on. You just sort of restructure this as a single vector, right? So when you're going backwards, if you obtain the derivatives with respect to these values, you can fold them back into these maps, and now you would have the derivatives with respect to each of these elements. So using the standard learning paradigm, the backpropagation paradigm, we now know how to compute the derivatives with respect to the outputs of all of the elements of all of the output maps of the final layer of these convolutional layers. And now, from there, we have to continue propagating the derivatives backwards, and that's where we need to make our adjustments. Now, what does that mean? There are two kinds of operations we had. One was the convolution, the other was pooling, right? So in a convolution layer, we first computed these affine maps from the inputs using a bunch of filters. And from these affine maps, we computed these activation maps. So at the final layer, you can assume over here that you have finally obtained the derivatives of the divergences with respect to these guys. That's the final collection of maps. Those derivatives must now be propagated backwards to compute the derivatives for these affine maps. And then from there, these derivatives must then be propagated further back to compute the derivatives here, as well as the derivatives for these filters, right? And so this is what we'll have to figure out. For the pooling layers is a simpler operation. Each input map to a pooling is going to create the output map to a pooling. For the pooling, it's a one-to-one correspondence between maps. So we can assume that backpropagation has obtained the derivatives all the way till here. We now have to figure out how to compute the derivatives going backwards. So this is what we will see. So assumption, we have already computed the derivatives with respect to the elements of the maps output by the final convolution or pooling layer, whatever we choose it to be. And that has been obtained through backpropagation through the MLP. Now, from there, we've got to figure out how to perform two operations, how to perform backpropagation through convolution layers and how to perform backpropagation through pooling layers. So first, let's consider this for convolution layers. Everybody with me so far? Questions? Okay, this is the easy bit, right? So let's figure out how to do this. Now over here, when you're performing backpropagation through the convolution layers, there are two steps here. First, we have to figure out how to backpropagate from here to here through the activation. Then we have to figure out how to perform backpropagation from here back to here through the filters to the previous layer. So those are the two components, right? We need to compute derivatives with respect to the affine elements of the affine maps, given their derivatives with respect to the activation maps. And then given that, we need to go back and compute the derivatives with respect to the previous layer maps as well as the filters. First things first, this is the easy bit. How do you compute derivatives with respect to the affine maps given the derivatives with respect to the activation maps? Now, as it happens, this is easy because the activation maps were simply obtained by applying an activation function pointwise to these z guys, right? So every y, l, m, x, y, which means to say the lth layer activation map, the mth activation map of the lth layer at position xy is simply obtained by applying an activation function f to the corresponding element of z. So if I have the derivative with respect to y, of the divergence with respect to y, how do I get the derivative with respect to z? Anyone? How do you get it? Peter? There was a rule that we called it. Say it aloud, please. Chain rule. So can somebody give me the formula? James. Okay, come on, guys. That's easy, right? I've given you the derivative with respect to y, right? I need the derivative with respect to z. In the forward pass, you've computed the z values, right? So to compute the derivative with respect to z, it's just the derivative with respect to y times the derivative of the activation function f prime at that z. Peter, does that make sense?
Yes.
Okay, you should have been able to answer it, right?
Yes.
Thank you. And you too.
Yeah, that's us.
Yes. All right. Now, so this we figured out. Let's look at the second one, right? So we want to go back from the z, derivative with respect to z, to compute the derivative with respect to the previous y. So during the forward computation, we computed the zln xy, which is the nth map of the lth layer at each position, by applying the nth filter. See this notation over here. Again, WL is layer, M is the index of the input map, N is the index of the output map. Okay, so M monkey and N Nancy. So these would be applied. This filter is going to be applied on the previous layer maps to compute the z's. And so now, given the derivatives with respect to all of these z values, we need to compute the derivatives with respect to all of these y values and all of the w values, right? So first, let's take a look at how you can, I'm going through this step by step, every single operation that we perform, right? How do you compute the derivatives with respect to the y's all the way back there? So in other words, I have the derivatives with respect to every element of every map over here. And there should be no doubt about how we got this, right? How am I going to push that back and compute derivatives with respect to every element of every map over here, right? So first, let's look at the dependencies, right? When I look at the dependencies, in order to compute this nth output affine map, which filter would I use? What would be the index? The nth filter, right? So I'm going to have the nth filter, and every channel, every plane of the filter is going to convolve with the corresponding channel of the previous layer. So every input channel is going to interact with the corresponding channel of the nth filter to compose the nth output map. So every input map contributes to the nth output map. Just simplifying the picture. So this channel contributes through this filter. So again, this is the first input channel. This is the nth output channel. So it's going to be, the interaction is through W1N. 1 means it's the first input channel, N is the output channel, right? This one is the mth input channel. It's composing the nth output channel, so it's interacting through WMN. But this is the dependency. So again, every one of these channels also contributes to every one of these output channels. So this is the complete set of dependencies, right? And now, when I'm back propagating, what am I looking for? I'm trying to compute the derivatives of this divergence with respect to the elements of a specific input map. So I only need to consider how this map links to the divergences. That is, these are the relationships. These are the dependencies that I must consider. And over here, so the mth input map is going to interact with the first output map through WM1. It's going to interact with the second output map through WM2, and so on, right? Now, each of these guys, but when I'm speaking of computing these derivatives, what am I really speaking of? I'm computing the derivative of this divergence with respect to every one of the elements of this map. That's what I want to compute, right? So we got to figure out, it's not just a generic map. How do I obtain the derivative with respect to every single position in this map? That's the arithmetic we want to figure out. Now, if I want to do this, if I think of this as, this map, this map influences every one of the output maps. So clearly, to compute the derivative of the divergence with respect to this guy, I have to sum over all of the output maps, right? And again, using the distributed chain rule, that's going to be the sum over all of these maps of the derivative of the divergence with respect to z times the derivative of z with respect to y, right? Is this correct or is the order wrong? Do I have to flip the order or is the order right? Can I hear that aloud? Is it right or wrong? It's good. Okay, good. Why is it good? You have to go left to right, right? As you go backwards, we keep adding things to the right. Remember? So now, in order to do this again, we already have the derivatives for all of these guys, right? So we assume this. So this term is given. What we need are the derivatives of the z's with respect to the y's. And so we need the derivative for every one of these z's with respect to the y, but let's just take a typical z. Let's consider this one. So we need to know let's figure out how to compute the derivatives of this z with respect to this y. By that, what I mean is, how do I compute the derivative of every element of this y, of every element of the z with respect to every element of that y, okay? So again, if I want to compute, because when I'm taking the derivative, performing the chain rules, going back, then I not only have to go over, this is not a simple dependency. Within this map is a collection of numbers, the z value at every position, right? So even within that map, I have a distributed chain rule. I'd be summing over all the elements of the z. And what would I be summing? The derivative of the divergence with respect to that element of z times the derivative of that element of z with that corresponding element of w, right? That whole operation would have to be performed. So let's look at how the elements of y introduce the elements of z, influence the elements of z. Let's consider a single y over here, element of y over here. And this is the animation we saw earlier. So let's just take a look at the boxed y element and see and determine which are the elements in z that it actually influences. And now an element in y influences an element in z if it is used in the computation of that z, right? Otherwise it does not. So here it is. So as you can see, as it goes forward, it's being used in the computation of the first z value, the second z value, but not in the third. Then going down, the first and second in the second row, and in the third row, it's not being used at all, right? So this guy is influencing these 4 elements in z. But this is just for one map, right? It's actually doing it for all the maps, but it's going to be the same 4 elements for all of these maps. And so this one term influences these 4 z elements for all the maps, but you can generally think of it as applying, in the most generic sense, every y element influences every z element or element of every z map. That's the most generic consideration, right? So when I want to compute the derivative of the divergence with respect to this element, I'm going to have to sum over all of the output affine maps. Within the output affine map, I'm going to have to sum over all of the elements within the map. And within each map, I'm going to be, the contribution of each element over here is going to be the derivative of the divergence with respect to that element times the derivative of that element with respect to the element in y, right? So the derivative of zx prime y prime with respect to yx phi That is the derivative we really need to figure out, right? Now, to see what this value is, let's actually take a closer look at convolution again, okay? Now, just to show you how the convolution operates, I've shown you a filter over here. The filter is both color indexed and position indexed. We will need both for the visualization. So you can see that it has 9 unique colors, and every position is also showing its index, its 0 index. So it's 0, 0, 0, 1, 0, 2, 1, 1, 1, 0, 1, 1, okay? 0, 1, 1, 1, 2, 1, 0, 2, 1, 2, 2, 2, right? And then different colors, and this is your Y map. Consider the central element in the Y map, Y22, and let's see which element of W interacts with Y22 to compose every one of the elements of Z prime, okay? Of Z. So to compute Z00, 0, I will be positioning the filter at the 0, 0 position of Y, right? And then computing the inner product. But when I do that, which element of the filter does Y22 interact with? Pardon me? 2, 2, right? So Z00, the contribution of Y22 here is Y22 times W22, okay? Now again, see the indices. This is the Lth layer Z. This is the L-1th layer Y, right? This is the mth Y channel, and this is the nth Z channel. So this is the nth filter and the mth channel of the filter, just to be clear, okay? Now, do you see a relationship between these indices? Anyone notice a relationship between the indices? Okay, just to show you again, I'm going to slide this and figure out how Y22 helps in composing Z10. For that, I have to move the filter over and place it at 10, right? So when I place it at 10, it is this element of the filter that multiplies Y22. And this element is W12, right? And it's composing Z10, okay? Now do you see the relationship between the indices?
So it's 2, 2 minus?
2, 2 minus? 2, 2 minus. So basically the index of the Z and the index of the W sum to give you the index of the Y. And this will always be the case, right? Check over here, 0, 0 plus 2, 2 is 2, 2, right? 1, 0 plus 1, 2 is 2, 2. 2, 0 plus 0, 2 is 2, 2. 0, 1 plus 2, 1 is 2, 2. 1, 1 plus 1, 1 is 2, 2. 2, 1 plus 0, 1, also 2, 2, right? At every single position, the index of the filter and the index of the output map had to give you the index of the Y element. So in general, I can say to compose Zx prime Y prime, I'm going to be multiplying Y22 with filter 2 minus X prime, 2 minus Y prime. Everybody see this, right? And so on. So I can generally say Zx prime Y prime, the contribution of any Yxy to Zx prime Y prime is going to be Yxy plus W x minus X prime, Y minus Y prime. Does everybody see this, right? It's visually apparent, so it doesn't need a lot of explanation. Now, what is the derivative of Zx prime Y prime with respect to Wyxy from this equation? Anyone? It's just the weight, right? It's there. DZ, somebody posted a meme about this. You know, the answer's on the slide and you look absolutely stunned. But anyway, the derivative of Zx prime Y prime with respect to Yxy is Wx minus X prime, Y minus Y prime. I'm not mentioning the layer and channel indices here. It's apparent, right? So, writing my derivative out, the derivative of the divergence with respect to Yxy, right? Overloaded symbols, but yeah, this is uppercase y, lowercase xy. It's going to be the sum over all the channels, and within each output channels, and within each channel, it's going to be the sum over all the positions of the derivative of the divergence with respect to that element of the output channel times the derivative of zx prime y prime with respect to yxy. That's just the distributed chain rule, which we know is simply going to be the weight at x minus x prime and y minus y prime, right? So if you simply implement this formula, you should be able to compute the derivatives of the divergence with respect to every element of the input channel, the mth input channel. So any questions, doubts? No? All right, yes.
I have a doubt regarding the shade parameters concept in this drawing.
Which one?
Shade parameters.
Well,
Which of these weights will be shared with you?
so we are not looking at the weights over here, right? I'm computing the derivatives with respect to y, right? We have not yet gotten to the derivatives with respect to weights. Those are shared, right? Because the same weight applies at various positions. So there you have the notion of sharing. But right now we are looking at the easier problem. What is the derivative with respect to y, okay? But polls. Five seconds, guys. Okay. Does somebody on Zoom want to take that first question? Anyone?
True.
True. Okay. And someone here want to take the second question? True. All right. So both are true, right? In order to compute the derivative at a single affine element, sorry, no, this is not a single element y, x, y. We must consider the contributions of every position of every affine mapper, the next layer. The derivative for a single, again, this term shouldn't be affine, element y, x, y will require summing over every position of every z map in the next layer. So basically here is the formula that we have. To compute the derivative with respect to y, x, y, we're going to be summing over all of the output channels. And within the each output channel, you're going to be summing over all of the positions of that channel. And the term you would be summing is going to be the product of the derivative of the divergence with respect to the z value at that position and the weight, which is the weight at zx prime minus x, y prime minus y. Again, this is secondary. So note this. I'm computing the derivatives for the mth input channel. And when I'm considering the contribution of the elements of the nth output channel, the weight that I'm going to be considering are the x minus x prime, y minus y prime element of the filter channel of the mth channel of the nth filter, right? The specific filter and channel that connects ym and zm, right? Yes, Eric.
Isn't it only partially true because the filter only has a certain size? So, you know, this pixel input won't affect this one on the output if the filter isn't big enough.
So this is a generic formula, right? So you have to imagine the filter as being much larger with all the other elements being 0. Right? Now, but this is actually a convolution. Does everybody see how this is a convolution? I don't think so. So I'll show you how it's a convolution, right? To see this, let's go back to our picture, okay? And for now, I want you to assume that this entry over here, first, let's see how the how the filters interact with the channel elements to compose the output channel, input channel elements to compose the output channel, right? So again, look at Z22, and now we're going to look at the color code, okay? So at Y22, So Z00 is obtained by multiplying Y22 with W22. So the term that multiplies Z, the term that is used in the contribution of Z00 is indicated by the color at Z00. So that's this 2-2th element of the filter. I've just put this color over here just to show you which filter element contributed to the computation of Z00, right? If I take a step forward, in computing Z10, the W12 element was considered. So I put the color of the 1/2th element of the filter at Z10. This is telling you which filter element was used in computing Z10. Then if I take one step forward, in Z20, I had to place the filter starting at 20. So now the filter element that's being used in computing it is this 0-2th element, which is this bottle green element, right? Now if I go down one step, Z01, I'm using this light green element, right? Which is the filter 2-1 that's being shown here. So is the visualization clear to everybody, right? So if I go forward this way, we are seeing every single element at each Z position. You're being shown the specific filter element that was used in computing it. What is the relationship between the color, set of colors over here and the set of colors here?
They mirror around the center.
It's flipped along X and Y, right? It's transposed in both directions, right? So in other words, in order to compute, if you want to see which element of filter element contributed to each Z, that is basically just a mirror image. But then how does that influence us? Now look at each element over here. Go back to the lower equation here. So Z00 is composed by the product of Y22 and W22. So the derivative of the divergence with respect to Y22 was the derivative of the divergence with respect to Z00 and W22. So now I want you to change your thought process and imagine that this picture is no longer the picture of the Z elements, but it's actually a map of the derivatives of the divergence with respect to the Z elements. Okay, so now you're looking at a map of derivatives, correct? So in that case, when I'm computing the derivative of the divergence with respect to Y22, the derivative, what does the derivative at Z00 contribute? The derivative at Z00 multiplies W22, right? To contribute to the derivative of the divergence with respect to Y22. The derivative at Z10 multiplies W12. The derivative at Z20 multiplies W02. And so on, right? The derivative at Z01 multiplies W21. At Z11, it multiplies W11. At Z21, it multiplies W01. At Z02, it multiplies W20. 1,2 multiplies 1,0. 2,2 multiplies 0,0, right? Everybody clear? Right? And so when you work the whole arithmetic out, this is the sum over this entire set of this entire map of the product of the derivative of the divergence with respect to every element in the map and a specific filter element. And what was the filter element? That is the filter element that you would get when you flipped the filter top to right, top to left, bottom to right, right? And where did you position the filter? This filter was positioned at 2, 2. See this? I'm computing the derivative at Y22, right? So in order to do this, I flip the filter both ways and position the top left corner at Z22. You see what's happening here, right? And then just took an inner product. Is the picture making sense to you guys, right? Visually, right? Yeah.
What if the case of like 0, 0?
We will get to that, right? And so the general thing is, if I want to compute the derivative with respect to yxy at any xy, I first flip the filter channel, again, this is the nth output channel. This is the mth input channel. So I'm going to take the mth channel of the nth filter, flip it left to right, top to bottom. Then place it at position xy of the derivative map for the affine values. So this one output, this is no longer the affine map, it's the map of the derivatives of the divergence with respect to these affine values. So I'm going to flip this position this transpose filter with the bottom right corner of the transpose filter, which corresponds to the top left corner of the original filter at xy, and then compute an inner product. And that's going to give me the contribution of this map to the derivative at yxy. So everybody clear? Right, okay. So what does this look like to answer this other question? How do I compute the derivative here? I flip the filter. I start off with this filter. The first thing I do is flip it, right? But then, remember what happened when we went forward, when we performed convolutions. We lost rows at the columns at the bottom and columns to the right, right? So we're going to have to record. So you had a certain number of inputs going in and a certain number of outputs coming out. So when you compute the derivatives backwards, the derivatives, you must compute the size must increase backwards. You should be able to get derivatives for everything that contributed to the output, right? So in other words, although the output was only this size, the input was this size. So when you go backward, you should be able to compute the derivatives for all of these guys, clearly, because all of them contributed to the output. What is the contribution of this? How do I compute the derivative here? To do so, I'm going to zero pad my derivative map with a certain number of zeros on every side. How many? I need to be able to position my flipped filter so that the transpose filter so that the bottom right corner sits at 0, 0 in order to compute the derivative here. So if the filter is some k cross k, how many zeros would I have to add on top and bottom? Top and the left. Someone. K minus 1 rows of zeros and k minus 1 columns of zeros, right? So that's what I've added over here. And now I can position the filter like so and compute the inner product, which is this value, right? Then to compute the derivative for the next position, I've just slid the filter forward and so on, right? I can keep sliding the filter forward in this manner to compute the derivatives with respect to every one of these guys. But observe something interesting happened right here. I didn't stop. I computed these 3 derivatives, but I didn't stop here, right? I also had k minus 1 zeros to the right. And that way, I could continue computing derivatives for as long as the transposed filter stayed within the derivative z map, right? If you go beyond that, I have a bunch of zeros, there's nothing to contribute. So this operation now, I can continue this all the way until I have at least one element of my transposed filter sitting on the derivative z map, right? I've added, now observe what happened here. So if I had my z map was, say, this is my z map, suppose this was m cross m, right? By padding k and my filter was k cross k, then I padded k minus 1 zeros over here, k minus 1 zeros over here, k minus 1 over here, and k minus 1 over here, correct? So what is the final size of this guy after padding zeros? It's, wake up guys, yeah, what's the final size? M plus 2 times k minus 1, right? 2 times k minus 1 plus m. What happens if I convolve this with a k size filter? What is the resulting size? Remember, when we convolved some image with a filter, we lost a certain number of elements, right? How many elements did we lose on the edges? If you had a k cross k filter and when we convolved it, how many elements did we lose? K minus 1, right? We lost K minus 1 rows and K minus 1 columns. So I've got this 0 padded entry, which is 2 times K minus 1 plus M. I'm convolving it with K. What is the size of the result? M plus K minus 1, right? Which is going to be the size of the input. Right? So I've expanded the thing by K minus 1 entries going back. I lost K minus 1 rows and columns going forward. I gained them back going back. Make sense to everyone? Right. But then this was just one channel, right? In reality, this position, any element over here affects all of the output channels. And so in order to compute the derivatives for any one guy over here, we'd have to consider all of the output channels, right? And now, if I'm looking at the mth input channel, so the mth input channel is going to influence every one of these output channels through the mth channels of the filter, of all the filters, correct? And so if I want to see how this element influenced all of the output channels, I'm just going to pick this row, this mth channel of every filter, and grab those. So these are the mth channels of all the output filter, all the filters. This is not a single filter. It's the mth channel of all the filters, right? I'm going to transpose those. And I'm going to 0 pad all of these guys. And then I'm just going to convolve. So this will be my new filter going back, which is basically a transpose of the filter that was going in, because now I'm using the mth channel of all of the filters, right? And constructing a new filter with it. I'm transposing it. And that's what I'm going to be convolving with the 0 padded output derivative maps. And that will give me the derivatives with respect to the input map, right? And so that's the overall, that's what the overall operation is going to look like. Make sense to everybody? Right? So the overall process, if I wanted to compute the derivatives with respect to the mth input channel, I had to get the mth channel of all the filters. I had to, and then I had to transpose all of these filter channels. That's going to be the equivalent of a backward filter. And now I'd be 0 padding the derivative maps of the outputs. And then I'd be convolving that using this transposed filter, right? So clear to everybody? I see some very big eyes. Okay, yes.
So to find the divergence in terms of y of the previous layer, for like the filters on the diagram are I guess in this diagram is the derivative of that blue square equivalent to all the squares in like the bottom right corner.
So this is okay.
That's not really.
Okay, this light blue square is going to be the map of the derivatives of the divergence with respect to all the elements of that affine map.
Yeah, it's divergence with respect to the.
Yeah.
Okay.
Right. So, okay. Everybody with me? Yes.
So we're looking like back convolution for all filters.
Correct. Back convolution of the mth channel of all the filters, right? Yeah. So the mth channel for all n filters to get the derivatives for the mth input channel, right? Okay. So, yeah. Anyway, and so the sizes will be right. Now, if the y map was 0 padded in the forward pass, the derivative map will be the size of the 0 padded map, because you're going to get derivatives for everything that was used. So this might have been 0 padded, so you're going to get derivatives for all of these guys. But we know that these shaded regions were just 0 padding, so you're just going to throw them away and just retain whatever was the non-0 padded region going forward. Here's your third point. Okay, 10 seconds. All right. Anybody want to answer this? Chanwu, what are the answers? What are the answers? Any of you guys? 1, 2, and 3, right? To compute the derivative with respect to the mth activation map of the Lth convolutional layer, you must select the mth channels of the L plus 1th layer filters, right? The next layer's filters. The selected filter channels must be flipped left, right, top to bottom, and they must convolve the derivative maps for the next layer affine values, right? So this is the computation to compute the derivatives with respect to the input affine maps can be computed using this equation. I have the pseudocode for it. Let's skip that. Now let's look at how we can compute the derivatives for the weights. That too is going to be a very similar operation. Now this is where the shared parameter business comes in here, right? So each weight affects several z values, right? So for example, look at the central dark blue thing. Now this color is bouncing back and forth because of MATLAB's craziness. But if you see this central blue element is used in the computation of every one of the outputs, right? So every filter affects every position, but only of a single output channel, right? A filter channel works only on a single input channel and is used only to compute a single output channel, but within that output channel it influences every single position. So to see how this works exactly, let's consider a single filter. Let's say I have this one output channel and I'm looking at how this input channel, the weights that connect this input channel to this output channel, let's see how it affects the individual elements of this guy, right? So let's say these are the weights. Now I want to compute the derivative I want to see how this pink element, which is the 1-2 position of the first channel of the first filter, right? So the first filter is going to be computing the first output channel. And I want to see how this influences the computation of all of the entries in the outputs. Now, is this guy going to contribute to any other output channel? No. Can everybody say no together just for my sake? No. Thank you, right? So now let's see how this works. This one, this W12 is going to be multiplying Y12 to compute Z00, right? What was the relationship we saw between the indices earlier? The Z index and the W index sum to the Y index, right? So to compute Z10, W12 is going to be multiplying W22, right? The same relationship holds at every position, right? So I can generally say Zxy at any xy is W12 times y x plus 1, y plus 2, correct? Because the indices of Z and W sum to give you the index of y, right? Or generically, Zxy, this has got to be plus equals, right? Is going to be, so there's a plus missing. Oh, plus extra terms over here, okay. So the contribution is going to be of any particular Wij to Zxy is that Wij is going to be multiplying y, x plus I, y plus j. Correct? That's clear to everybody? And so now, if I want the derivative of Zxy with respect to any Wij, that's going to be, what's that going to be? Can someone answer me aloud so I can hear it from here? Y what? Y of x plus I and y plus j, right? And why is that, Fazan?
Because there's this because it's a chain rule, so your derivative is essentially just the output because they're driving with respect to with the weights
Okay, but how did you arrive at the indices?
by summing the z value with the y value.
So the derivative of z of zxy with respect to wij, we know that the index of y that multiplies any w to give you any z is the sum of the indices of z and w, right? So the derivative of zxy with respect to wij is going to be y of x plus I, y plus j, right? And now, of course, if I consider any particular filter element, each filter component is going to be contributing to all of the output affine values, right? So if I want to compute the derivative of the divergence with respect to, say, the ijth element of the filter that connects the mth input channel to the nth output channel, that's going to be the sum over all the elements of the nth output channel of the derivative of the divergence with respect to, so you can think of this as the derivative map, the derivative of the divergence of the derivative of the divergence with respect to that element of the output channel times the derivative of the element with respect to the corresponding weight, right? So the derivative of the divergence with respect to wij is going to be the sum over all xy, all elements of the output channels, time of, and the sum is of the derivative of the divergence with respect to zxy times the derivative of zxy with respect to wij. And what was this? Do we have this element already, the first term? Right, because we've been going backward, right? We assume that we have the derivative with respect to z. What is the second element here? Can somebody, okay, I'm going to call on someone, Nate, you, actually Rebecca, you, and you're going to tell me what this thing is really loudly so the guys can hear us in Silicon Valley.
It's y, and then it's the parentheses L minus 1 mx plus I and y plus j.
Thank you, right? That's how enthusiastic I want you guys to be. You have to be heard halfway around the world, don't forget. People are listening to you in Kigali. If you mumble, it's no use, right? So this term is already computed. I can just plug this in, and so that's my formula. Everybody with me, right? I can just plug this formula in and I will get my answer. But then this is my overall formula for computing the derivative of the divergence with respect to every element of every channel of every filter. And that's the sum over all the elements of the output channel that the filter composes of this product of the derivative of the divergence with respect to the element and the derivative and the y, the input element that connects the two, right? But this is just a convolution. And if you don't believe me, let me show you how this works. So I can, and this is in fact, what is it a convolution of? It's even simpler than the convolution that we had to compute the derivatives of the inputs. So when we were computing the derivatives of the inputs, we had a negation. It was I minus x, j minus y. Here there's no negation. Here it's x plus I, y minus j. So each filter over here in the forward computation is going to compute one affine map, right? And if you consider one channel of any given filter, this channel convolves with the corresponding input channel to contribute to the output affine map corresponding to the filter index, right? So to compute the derivatives of the divergence with respect to this filter, we can ignore everything else because those are the only two relevant maps for this particular filter, right? And so let's just focus on these two guys. Let's throw the rest away. So that's this one. But then what do? This over here is my derivative map. It's not my affine map. It's the map of the derivatives of the divergence with respect to these affine values. And in order to compute the derivative of the filter, the derivative of the divergence with respect to this filter, all this formula tells me is that I must convolve the input channel with the derivative map for the output channel. So literally, I just place that on the top left corner, and I'm going and compute an inner product, and I'm going to get a derivative for the filter at the top left corner. Then I slide the whole thing forward, I get the derivative for the next element, and so on. And so this is how I'm going to actually obtain my derivative. It's a very simple convolution. So as you can see, the computing the derivatives for the filters is even simpler than computing the derivatives for the inputs themselves. And again, you can see that the sizes match. If the output over here is, say, m cross m, the input is n cross n, then what is the size of the convolution? It's going to be m plus n minus 1 times m plus n minus 1, right? But then that will be the size of the filter itself. You can just work it out. Just look at the visuals should make it amply clear that you're going to get the correct size of the derivatives for the filter. Again, I'll let you work out the arithmetic. The point is it's very simple. It will be correct, right? And so to compute the derivatives with respect to every one of the filter channels, I just need to convolve every one of the input channels with respect to the derivative map for the affine for the output channel of the convolution, right? So, and again, if y was 0 padded in the forward pass, it must be 0 padded for back prop as well, just to make sure that all the sizes match. So every operation that you perform in the forward pass must be performed in the backward pass. Right? So okay, 10 seconds. All right, let's pick someone over here to answer that question. So you guys at the back. The person behind Fazan, I don't know your name. Just the first one. What was your name again? Sam. All right, thank you, Sam. Just the first one, right? The derivative for the mth plane or the mth channel of the nth filter is computed by convolving the mth input channel with the derivatives map for the nth output channel, right? So easy. I have pseudocode for it, but skip the pseudocode going backwards. So we can just perform this. But here's an even simpler trick. If I can take a couple of seconds for this, you don't even have to worry about convolutions, flipping, and such like. It's much easier when you see through the lens of code. How so? So firstly, for any computation of the form y equals sigma x, dl over dz is going to be dl over dy times dy sigma prime z, right? Sigma z. So this z should have been below. For any computation in the forward pass of the form where z plus equals wy, right? Then I can say dl over dy is going to have an additive contribution, which is y of dl over dz, and dl over dw is going to have an additive contribution, which is so dl over dy is w times dl over dz, and dl over dw is going to be y times dl over dz. So do you see how these equations work out, right? These equations make sense to all of you? May I hear an enthusiastic yes? Yes. Thank you. So that's easy, right? Now here's how I'm going to use that for a cheat. This is my forward computation. I'm going through all the layers. Within each layers, I'm scanning from in left to right, top to bottom. At each position, I'm going through all of my output filters, right? So let me actually draw this. I will I mean, folks, I may go 2 or 3 minutes over. I'm being slow, but that's okay, right? So I have all of my input channels. And so I'm going to be at each position as I scan, we are sort of applying the filter to all of these guys, all of the input channels, right? And so this one here, as I'm scanning left to right, I'm computing all of the output channels. So this 1 to DL loop is basically looping over all of the output channels. Within the output, within each element, so at each position, I'm sort of taking the inner product of the filter and the underlying Y position, right? And summing them all up. And then finally, I'm applying an activation to it, right? So I've just drawn this at the top left corner, but this could be at any position. Now to compute the derivatives, I'm just going to use these rules. Remember, this is backprop, right? So I'm going to go unwind. The order of the loops stays the same, but within each loop, I'm going to go instead of from the top to the bottom, I'm going to go from bottom to top. So this one is now going to go, this would be going from L to 1, right? You're going from the outermost layer to the innermost layer. And then within each position, instead of going from 1 to the final position in X and 1 to the final position in Y, I'm actually going to go from the final position backward to 1 along X and then also along Y, okay? Then instead of going down these filters from top to bottom, as I'm computing them, I'm going to reverse the order, bottom to top. All I did was reverse the indices, the order of the indices. It's still the same code, right? And then over here, within each of these guys, the last operation I performed was computing the activation, right? So the first operation I'm going to perform is going to say derivative for Z is derivative of Y times the derivative of the activation, right? That's all I have done over here. Then within each loop, I went over all of the input channels, right? So here I'm going to go over all of the input channels, but in reverse order. It doesn't really matter, but just for consistency, I'm just reversing the order, okay? And then here I'm going from beginning to end, top to bottom. So I would actually be flipping that order too. Some of these reversals are not really important, but we're just staying consistent because it's back propagation. And then we are down to the innermost loop, right? Which is Z plus equals W times Y. So all I have to do over here is within the innermost loop, I can say d of y plus equals dz times w, d of w plus equals dz times y. Right? I literally just took the code and flipped the order of operations. And I used the simplest of rules, which was this rule, to break things down. Right? And this will give me the correct answer. Of course, I have to embed this within the layers loop as well. So this making sense? But this is very mechanical. You don't even have to think about it, right? That's exactly how the operations are performed going forward. So I can unwind the whole thing and perform the operations backward. The one thing you do have to worry about is that the derivatives that accumulate, so you'd have to initialize these derivatives as zeros, and all of these are plus equals rather than just merely equals. And there are multiple ways of recasting this tensor vector operations. So we figured out how to compute derivatives for all the convolutional maps, right? So this is done. We are left with pooling layers. Now for pooling, we were trying to introduce jitter sensitivity, reduce jitter sensitivity. So we were performing a max operation, right? But when we performed a max operation, what did we do? We took the maximum element of all of these guys. So if I had this element 1, 3, 6, 5, the output is going to be 6. Now, in order to compute the derivatives, you have to go back and think about what does a derivative really mean. A derivative basically tells you whether perturbing an input is going to perturb the output, right? So in our case, our final output that we are trying to minimize is the divergence. Over here, if I perturb this value 1 by a little bit, Is it going to change the divergence? No. So what will the derivative with respect to 1 be? What about 3? 5, 0. So the only thing that we have to worry about is the derivative of the maximum value, right? And what is that going to be? No, so I'm speaking of the divergence, right? So basically whatever I had over here at the output, this guy, so this is just a scanning operation. So whatever derivative I had over here is simply going to go into this position, right? Now this is why when we were doing the max pooling, we were retaining information about which position we were reading the maximum value from, because when you go backwards, you're simply going to copy this derivative into that position. Making sense to everybody? Right? So easy, right? Nothing complicated at all. And so when I write the pseudocode, here was the forward operation for max pooling. This was being done independently for every channel. Within each channel, you were scanning left to right, top to bottom, finding the position of the maximum in the value, and then copying the value over. When you go backwards, all we are going to do is going to copy the derivative of the divergence with respect to y into the corresponding position, into the position of the maximum value in the input. Okay, but there's one little tweak over here. There's a plus equals. Why is that? Why do I have this a plus equals? Anyone? As I'm scanning, why do I have a plus equals here?
The same input can be the max for multiple.
Because the same value could be the max for multiple output windows, right? And so if it's contributing to multiple outputs, all of them must be summed. Making sense? Right, okay. And so what about mean pooling? So this is making sense to everybody? Right. What about mean pooling? In the case of mean pooling, we were computing the average of all of these guys, right? This is like saying that this tau O equals this, the y O equals, in this case, 1/4 times y1 plus 1/4 times y2, and so on, right? So if you look at this, dl over dy1 is simply going to be dl over dyo times 1/4, correct? Straight up arithmetic. So this means that when I compute the derivatives going back, I'm just going to take the derivative of that position and distribute it uniformly over all of the elements that contributed it. Make sense? Right? And so the pseudocode over here is simply going to be, this was the pseudocode for the forward operation. You were scanning the input, and at each position you were computing the mean of this block. Going back, you would just you would grab the derivative for the output and distribute and divide it by the size of the block, which is going to be k squared, and add that to the derivatives at each position in the input that was used to compute it. Again, this is a plus equal to, because each position could contribute to multiple windows if the adjacent windows overlap, right? And so when I'm learning the networks, we've seen how the derivative of the divergence with respect to every intermediate value and every feed parameter can be computed. We can embed this in gradient descent to learn the network. We're still missing one component, resampling. We'll deal with that in the next class. So the story so far, convolutional networks are supervised versions of computational models of mammalian vision. They include convolutional layers comprising learned filters that scan the outputs of the previous layer, and pooling layers that operate over groups of outputs to reduce the to introduce jitter and variance. And the parameters can be learned through regular backprop. Max pooling layers only propagate derivatives over maximum elements of each pool. Derivatives must sum over appropriate sets of elements to account for the fact that the network is in fact a shared parameter network. So that is that. I'll see you in the next class. Do we have the attendance sheet? Have all of you signed the attendance